Hey CP class, let's go ahead and look at problem solving today, a little more in depth, problem solving using Newton's laws. And in particular, Newton's second law. It's not that the other laws don't come into play, they do, but Newton's second law is where we're going to focus because most of these systems will be accelerating. Some of them will not be though. So, and that's just in general, mostly Newton's second law, F net equals ma. Hello, I know you knew that. F net equals ma is our second law, but we will definitely be looking at forces being balanced. This thing's going haywire. There we go. We'll be looking at forces being balanced, like we've been talking about in some of the warm-ups. In that case, we're looking at the first law because we're talking about if there's a balance of forces, the thing's going to remain in the state of motion that it's already in. And then maybe we'll get into some third law stuff, which is every action, there's an equal and opposite reaction. So the first one, number one, we're going to look at weight. And in parentheses next to weight, I'm putting the term that everybody knows, gravity. Gravity and weight are the same thing in these problems. There's no difference. So your attraction to the earth, your gravitational attraction, that is your weight. And we're going to be looking at normal force. So both of these ideas. So let's start with a very simple problem, and this one will not be using Newton's second law, but the ones thereafter will be. Let's just draw a box. One of the simplest things we can draw is a box on the ground. Now be the box for a second. I want you to pretend like this is you. You. What do you feel? Well, you feel attracted to the earth because you're obviously on the ground. So you must feel pulled down to the ground, and we're going to draw an arrow down from you, the box. And let's say, let's call it F sub G for gravity, force of gravity, right? And then we're going to also realize that if this was the only force on our drawing, that would be an unbalanced force, wouldn't it? And what you would do is you'd go crashing through the floor because there's nothing balancing you out. All you have is a downward force. Again, that's what we've been talking about in the warm-ups. If you have an imbalance in your forces, you're going to accelerate in that direction. However, we know that this box doesn't actually crash through the floor. Most surfaces are strong enough to hold a box because what the surface does, it pushes back. The surface actually pushes back with a force that I'm going to call F sub n. Now this is the normal force. So next to this, I'll put normal force. And by the way, down here, I'm going to put that this is gravity, otherwise known as, I already said it, otherwise known as weight. Same difference. And I need to define both of these. So this is kind of a mix of doing some math solving and then also looking at some definitions along the way. Because if I just give you definitions, that's a super boring lesson, right? Okay, let's stop joking around about this being you, and let's actually give this a certain amount of kilograms. So I'm going to say that this thing is, let's say 5 kilograms. No, let's go 50. Let's make it 50 kilograms. So I'm just going to kind of write over the top of that and just know that that is a 50 kilograms. 50 kilograms. Okay. Now, what I want to do in this drawing is figure out the value of both of these forces, and we can do that pretty easily because the force of gravity is always equal to the following equation. It's always equal to mass times little g. Always equal to mass times little g. In fact, as we do more problems, I'm going to stop writing Fg and I'll go straight to writing mg, meaning mass times little g. Now this right here is not gravity. This is the acceleration due to gravity, right? That's the free fall acceleration that we've been talking about. So don't call little g gravity because it's not. It's the acceleration of gravity. Fg is the gravity. That's the actual force, which is equal to this simple little 2-letter equation. So let's find it. We can find it right now. We'll say 50 kilograms times, now hold up, don't put a negative. Leave it as a positive 9.8. Leave it as a positive, and I'll explain why in just a second. If you do this math, you should get 490, I believe, 490 newtons. Yes, that is the answer. So that's your gravity. That's your weight if you're that box. Now, again, I'm going to come back and actually give you formal written definitions for both of these forces, but let's first find the values. So we're done with gravity. What about the normal force? Let's talk about what normal force is a little bit. Again, it's the surface pushing back. So if you set something on a surface, the fact that it doesn't crash through that surface is because the surface is pushing back. And notice the surface pushes back at what angle relative to the surface? So there's the surface, right? And there's the force. And what's this angle right here? It's 90 degrees. The normal force will always act at 90 degrees to the surface. It will never act at an angle to the surface, always at 90 degrees to the surface. Well, let's go back to Newton's first law for a second. This thing's not moving, it's at rest. And if something's at rest, it means that the forces must be balanced out. Well, what are the forces so far? It's just these two, that's it. So my down force has to equal my up force because this thing is at rest. So I'm going to say here, because system, you could say box if you want, is at rest, forces are balanced. In y-axis. If you notice here, there are no x-axis forces. No one's trying to push it from this side or this side. There's only y-axis forces. So those forces must be balanced. What am I trying to say to you? I'm trying to say the following, that forces up, put forces up equal forces down. Okay, forces up equal forces down. So let's go ahead and plug in our force up. And notice I put plural here, because sometimes there is more than one force acting up, and sometimes there is more than one force acting down. But the only force acting up is Fn, so I'll write Fn. And that must be equal to Fg. And Fg, well, we already found it. How did I find it? Again, it's that simple little equation I just showed you, mass times little g, and that ended up equaling 490 newtons. So all of this is a true statement. Fn is equal to 490 newtons, and so is Fg. They both are. Now, a moment ago, I said, don't worry about putting a negative here. Here's why. When we get to force problems, you've heard me say this already, whatever the dominating direction is, whatever the strong direction is, I like to call that positive. And whatever the weaker direction is, meaning the forces in the other direction are lesser than the other forces, I like to call that the negative direction. So I like to be able to pick what I call positive and negative when I'm doing force problems. So that means if I have stronger forces to the left, I'm going to call left positive. If I have stronger forces acting down, I'm going to call down positive. So I'm going to kind of flip the script a little bit here, because in kinematics, we're very specific. We always say left is negative, right is positive, up is positive. Did I say that right? Right is positive, left is negative, up is positive, down is negative, right? But you're going to see a lot more freedom with that idea when we do these problems. So the point is, the reason I said all of that is because I'm saying we don't want to just call this negative 9.8. We just want to use the value, because sometimes I'm going to decide to call the down direction the positive direction because it will dominate over the upward direction. In that case, the object would move down. And I'll show you a problem like that a little bit later. Okay, that's done. Now let's get back to that other thing I said we had to do. We got to define these two terms. So the normal force is the support force that the surface provides on the object period acts meaning it engages at 90 degrees to the surface. I didn't plan my space well there, but I'm sure you are able to fit it because you don't have a big fat pen that you're writing with, right? Acts at 90 degrees to the surface, and that's what we're talking about up here. It's always acting at 90 degrees to whatever surface. So when we tilt the surface in problems later, when we get into 2 dimensions, when we put an object here like this, like that's a box, I know it's a pen, but pretend like it's a box, right? The normal force is not acting like this, it's acting like this. Because isn't that 90 degrees to the surface, right? So that's what normal force is all about. It's the surface pushing back on whatever is pushing on it. Gravity or weight. I don't have enough room here, so I don't know, maybe I'll just put it off to the side here. If you have room, please write it underneath here, but I'm going to go ahead and do it off to the side, maybe like right over here. Okay, gravity. What is gravity? Gravity is the force of attraction, and by the way, it's always attractive. Gravity is never repulsive. Magnets are repulsive. Charges can repel each other, but gravity never repels, it only attracts. Gravity is the force of attraction between an object and the earth, right? Like, yeah, I knew that. Yeah, I figured you did, right? It's what it is. Force of attraction between an object and the earth. But here's what's going to cook your brain. Here's 2 objects. Now this is no earth, but this is definitely an object, right? Do these 2 attract each other? The answer is yes. Any 2 masses attract each other. That's what gravity really is, which is a weird thought because obviously, forget the candle for a second. Here's a pen. Am I running into the pen? Am I attracted to the pen? No, because the force of gravity is so weak between me and the pen. It's really weak because, let's face it, this is not very massive and I'm not very massive. But when you get something as big as the earth, when you get a mass that kind of size, you can start to really attract other masses. So for now, this is our simplistic definition of gravity, and it works. Remember, gravity is also called what? Weight, right? And its equation is m times little g, which we put in a positive little g for. Okay, so I've took my time through all of that. I hope that makes sense. That gave us 2 new ideas, and it allows us to move on to the next problem. So let's go on to number 2, and we're going to look at something we've already been looking at, but I'm going to expand it a little bit. So let's just look at horizontal acceleration. I'll write it as horizontal acceleration. You've already seen 2 problems like this, so here's a third. Horizontal acceleration. Okay, I'll set up a pretty simple problem with a car. I'm not even going to write a question. I'm just going to put values on the drawing, and that should be enough for us to figure out what we need to do. So I'm going to make the car 5 kilograms this time. And let's go ahead and have a force forward of 20 newtons. And I'm going to call this F sub A and give you a new term here. This will be called an applied force. Now, whenever you see me write applied force, it's just a general force. This could be someone pulling the car. If I put it behind the car, it could be someone pushing the car. An applied force is just a general way to refer to a force that's being exerted on an object or a system, right? So I'm not even going to define that. We're just applying a force. And that will be worth, let's see, let's go 20 newtons. We'll keep this one really straightforward. And let's say that there is a backwards force. There's another kid pulling on this little toy car. They don't want their brother or sister to have it. And we'll call this, I'll call this one FA1, and I'll call this one FA2, right? And let's say FA2 is quite a bit less. Let's call it 10 newtons is fine. I should have drawn it a little shorter. If that's 20 newtons, then that should have been a little shorter for 10, but it's close enough. And what do I want to find here? Well, I want to find acceleration. Same thing that I've been looking for in all the other problems. So here's our last really straightforward, easy problem. The other ones that build off of this won't be super hard, but they will make it, they'll be a little bit more challenging than this. We're going to say, well, if I'm looking for acceleration, I need to do what? I can no longer use Newton's first law that my forces one way are equal to my forces another way. I must say F net, there must be an imbalance in the forces that is causing a mass, hello, to do what? To accelerate. F net equals ma. Unbalanced force equals mass times acceleration. What is my unbalanced force? Well, isn't it a combination of both of these forces? It is. My unbalanced force, F net, you need to see it one more time, which is okay. That's what F net is. It's an unbalanced force. It's the sum of all the forces. Here we go. It would be FA1 minus FA2, wouldn't it? Right? Because FA1 is obviously bigger than FA2, and that would equal mass times acceleration. Let's come up here and use this space. What would I do with my mass? I would divide it to both sides, wouldn't I? And cross out, right? And I would have FA1 minus FA2, all divided by mass, is equal to my acceleration. So let's plug in our numbers. And you'd have that, right? And acceleration would end up equaling 10 divided by 5. It'd be 2 meters per second squared, just like that. Now, which direction is it accelerating, guys? It is accelerating in whichever direction the big force is, right? Which direction is your unbalanced force or your sum of the forces? It's to the right, isn't it? These are your individual forces, but together they make up a unbalanced force, F net, that is equal to how much again? How much was that right there? Wasn't that 10 newtons? I'll put 10 right above that. If you do 20 minus 10, you get 10. Right? Don't make this a habit of drawing F net above the picture because it might confuse you, right? F net is the result of both of these. And that's what it would look like if we wanted to draw it. All right, so you're like, yeah, I already knew all that. Like we did 2 problems like that. I get it. Well, what we haven't talked about yet is the fact that there were forces acting in the y-axis also in those problems. And we just discussed what those were, didn't we? Isn't there a force of gravity acting down? And I'll try to squeeze that in here, Fg. There's an Fg, right? And there's also a support force from the ground that's pushing up on this thing called Fn. You might want to make your forces a little bit longer so you can see them, but there they are, just like that, right? And this is getting crowded. So what I'm going to do for the sake of you being able to see it is I'm going to redraw just the forces without the numbers. Okay, got my FA1. If your drawing is already clear, you do not need to redraw this at all. I'm just redrawing it for the sake of what I'm going to show you next. There's our force of gravity. And then there's the surface pushing back on the cart, Fn, the normal force. Is Fn equal to Fg? That's my question to you. Is Fn equal to Fg? Yes. Even though it's accelerating in the x-axis by how much? 2 meters per second squared. Is it moving in the y-axis? Is it rolling along and bobbing up and down? Is it levitating off the ground? Is it sinking into the surface? No. In the y-axis, it's actually at rest, right? So is it true that Fn equals Fg? Yeah, it is. In this problem, it is. And we already handled these 2 forces. We did F net equals ma with these 2 forces to find acceleration. Now, what do I call this when I draw all of the forces on a picture? This is called a free body diagram. And I'm going to be referring to free body diagrams. Oof. Free body diagram, that says diagram. I'll be referring to that term all the time. I can't live with that. I just can't. I won't do it. Free body diagram. And now my quick definition of this is a, guess it's a diagram of all the forces acting on an object. All the forces acting on an object. And this is really the first step for any force problem. Before you get into this equation, or before you start saying Fn is equal to Fg because in the y-axis it's at rest and those two forces are equal, before you do any of that, you just draw your forces in, because it starts to help you analyze the problem so that you can start making statements like this. And this, by the way, is for the x-axis, right? That F net equals ma was for only the x-axis. And I could also make the statement off to the side, hey, Fn equals Fg if I wanted to. That's true also. That's Newton's first law, right? Whereas that's Newton's second law. But all of these ideas come from me first drawing this picture and realizing, hey, my right force is bigger than my left force, but my up force is equal to my down force. I think that is good for that. You notice I'm explaining things more than once, right? The last, the last assessment showed me that that's necessary, and that's fine. Let's get on to the next thing. We're going to look at another problem, but this time let's do it in the vertical direction. So let's look at, let's see. Deciding. You know what? I have a better idea. Let's do one more horizontal problem. So we're within number 2 still. So we did number 1, which was weight and normal force. We did number 2, which is horizontal acceleration. Let's do another problem. In fact, on that last problem, why don't you put an A in front of that? So if I go back to that last problem, let's find it here. I would call this problem A, right? And now let's do problem B. Problem B coming up. This time I'm going to not give you one of the forces, and we're going to have to find the force. So let's make it something different this time. How about a fat baby? There's the bonnet. All my fat babies look the same. Fat baby on a sled, right? That's normal. Actually, for my friends, it was. They took their, gosh, the baby couldn't have been more than 6 months old, snowshoeing in the middle of Yosemite in the winter. They took their baby snowshoeing. That is the kinds of friends that I have. They think it's a good idea to take babies in the snow. It's still alive. It's doing great. It's now, I think that the kid is now like a teenager, kind of like you guys, maybe a little younger, maybe middle school. So we got our baby here, and there's a rope. Oh, I'm going to introduce a new force to you. How exciting. There is a rope. I'm going to put your rope, right? And when we pull on a rope, we call that force a force of tension. So I'm going to put F sub T, and that is tension. And let's define it right now. This would be a force acting along a taut. Now, I don't mean like how you're being taught by me right now. When I say taut and I spell it like that, it's like a tight rope, a rope that has no slack, right? You're pulling hard on it. A force acting along a taut rope, string, or cord. And we call it tension. Could you call that applied force? Yeah, you could, but Normally we refer to it as tension if a string or a rope is involved. So there's that force. Now I also showed you another force today in the warm-up, and that was the force of friction. So I'm going to put here friction, and I use a lowercase f for friction. And in this case, let's give you, yeah, you know what, I'll give you tension. So let's say that tension is equal to, in this problem, 50 newtons. All right, it's equal to 50 newtons. And let's say this whole system, and you keep hearing me say system because sometimes we're dealing with more than one mass. And here we have two masses together, a sled and a baby. Let's just say the system altogether has a mass of, what would be reasonable, maybe 10 kilograms, maybe 15. Let's go 15 kilograms. This whole system is 15 kilograms for its mass. Now notice I'm not giving you friction, so I'm going to write here, if tension is 50 newtons and the baby sled system accelerates, let's make it dangerous. Let's make it like 10 meters per second squared. That's like free fall. Can you imagine pulling a baby that fast on a sled? Your baby would get taken away from you, right? So the baby sled system accelerates at, I should have said at 10 meters per second squared. What is the frictional force? I want to find that frictional force, okay? So this is the first time where I'm actually giving you acceleration and I'm asking you to find a missing force. We don't know what the force is, but we definitely know how friction behaves. It's always acting opposite to the way that I want to move something, right? It resists motion. So for now, because there's a whole lot more friction than what I'm about to say, but for now, we can just think of friction as a resistive force. I could put that here in the column. I'll say friction is a resistive force. Resistive, yeah, force. And that's good enough for now. It's always resisting the motion. We're trying to move right. In fact, we are moving right. And the acceleration, I'm going to draw another arrow up here, and you'll see me do this quite frequently. Please do not, listen. Please do not think that this is a force I just drew. This is not a force vector. All the forces are right here. This is the what vector? The acceleration vector. That's the arrow indicating that I have a rightward acceleration at 10 meters per second squared. You don't have to draw that, but I'm just reminding you we're accelerating that way. Okay, now let's get into the equation we should use. Can we use the first law? No. This baby will not stay in a state of rest. This baby will not stay in a state of constant velocity. The baby will not be at rest or constant velocity because these forces are imbalanced. How do I know they're imbalanced? Because we don't know what friction is, right? I didn't tell you friction is 50. Friction was 50, we'd have 50 and 50, and this object would either be at rest or moving at a constant velocity. But we know, listen, that friction has to be less than tension. Why? Because I'm accelerating which way? To the right. And if I'm accelerating to the right, that must mean my rightward force is bigger than my leftward force. All right, I'll say it again. Since I know that I have an acceleration to the right, that must mean that my right force is bigger than my left force. So I'm going to go to the only equation that makes sense to use, F net equals ma, right? Okay, so let's plug in. I'm going to stay super generic, right? I'm not going to put in any numbers. What force is pulling it to the right? Well, that's tension. What force is pulling back the other direction? That's friction. And that all together is equal to ma, right? Let's solve for the thing that we don't know, because this time we actually know acceleration. Let's solve for f. Right now f is subtracted, I will add it. And what will I do with MA? I will subtract it to this side. Now, if that doesn't make sense to you, I'll do it one step at a time. I'll have FT equals MA plus F. Now you can see there's a plus happening between the MA and the F, so what am I going to do with the MA? I will subtract it. And I will end up getting FT minus MA, right, equals F. But I don't want to write it over there. I'm going to write it over here, equals F. Let's see what we got. 15 newtons minus my mass, 15 kilograms, times acceleration. Ooh. I want you to make a slight change with me real quick, okay? Please and thank you. Change this 50 for tension, because otherwise we're going to end up with a negative answer, and I don't want that. Change this FT to 500 newtons. Change it to 500 newtons, okay? So we're down here. You're changing this to 500 also. This says 500. Yes, now it will work. So down here, what are we plugging in for FT, not 50? What a silly idea that was. Let's make it 500 newtons. For FT minus 15 kilograms times how much acceleration? 10 meters per second squared. And what do we end up getting here? 500 minus, we know that this would be 150, right? So would you end up with 350? This would be 350 newtons. What? A newton? How did you get that? Kilogram meter per second squared. What is a kilogram meter per second squared? Guess what, folks? That is a newton. So really we have newtons minus newtons right there, 350 newtons. So that's a lot of friction, right? And I'm just making sure that all of this came out correctly. Yes, yes, and yes. Okay, yeah, it's all good. There's my friction. So if I went back up here, I could put in 350 for the friction, but you don't need to. Okay, so you got introduced to a new force, tension. You also got to see your first FNet problem where I didn't give you acceleration, and instead we had to solve for one of the missing forces. How did we know that this force was bigger than friction, and therefore this force, which is bigger than friction, should be written first? How did I know this force was bigger than friction? Because I was accelerating which direction? To the right. I would only accelerate right if the rightward force was the big force. So I knew to write this force first and then subtract friction. All right. Okay, now you might be wondering, well, what happened to kinematics? I missed those already. I'm sure that's what you're thinking. Well, what did we just do? We found a force. I could go on and ask you a kinematics question very easily. I could say, if the baby and sled started from rest, let's do it. If baby started from rest, and she, let's make it a she, and she accelerated for 8 seconds. What is her, do you want to find time or displacement? Let's make it easy on ourselves. Let's find time. What is her time? So we can very easily now shift over to a kinematics problem just so you can see this stuff is not going anywhere. We're still going to use it. Well, what are my givens? Notice this is how we start a kinematics problem. We always write givens. How do we start a force problem? We draw a free body diagram. Given. We have time, 8 seconds. We have acceleration from the first part is 10 meters per second squared. And also, we have that she started from what? She started from rest, so her VI is 0 meters per second. And we're looking for what is her time. Oh my gosh. This is why you don't make notes past 11 o'clock, which is what it is right now. What is her final velocity is what I meant to say. You were probably confused. Know that on these video notes, that if I make too many mistakes, I just start the notes over and you never see the mistakes. But if there's simple mistakes like this, I'm going to expect you just to flow with me, okay? Just know that I will catch it and fix it. If I don't, and you catch it, then let me know, and I will go back and see if you're right. But anyway, what is her final velocity? So we're looking for VF. VF equals, I don't know. And right now you can see the only thing I don't have in this list is displacement. Therefore, I need to use the displacement independent equation, which is VF equals VI plus AT. VI is 0. VF would simply be the multiplication of 10 meters per second squared, that's my acceleration, times my time of 8 seconds. Cross it out, and you get a dangerously fast speed. Wow. That's ridiculous. Yeah. Don't do that to a baby. But there you go. There's some kinematics along with that problem. And, you know, these notes have been going on for a while. So this next one I'm going to go through very quickly. There's going to be less explanation. It's more just going to be an example problem to have in your notes. Let's write number 3, vertical acceleration. So this would be a system undergoing vertical acceleration, 3. And we're going to look at a bucket and a well. And so if you need to rewind or pause at any point, because I am going to move pretty quick on this, right? Here's my well handle, right? And I can crank it up, and there's a bunch of rope. And then there is the rope attached to that bucket I was telling you about. And that bucket is 5 kilograms. And these come down, 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 and maybe a little lower. And we're going to have a well here, right? And this thing's going to descend into the well like that. There's some grass, right? I thought you said this was going to be fast. Well, can you draw this fast? Maybe, right? Okay, maybe a cattail. There we go. Cool. So there's my well. And I got my bucket right here. Now the bucket is not on the well. It's descending into the well. It's moving down. What would make a bucket move down? I wonder. Gravity. How about gravity, right? So gravity would be down. And think about it though, you're the bucket. What do you feel above you? Is there any slack in this rope? No, it's a tight rope. It's taut. And therefore, there is a tension up. There is an F sub T up. Now notice I made FG longer than FT on purpose. And our job in this problem is to find FT. So I'm going to say here, find FT. Find FT. Now I will tell you this, if the acceleration is, let's make it 2 meters per second squared. We've been using that value, 2 meters per second squared down. So this whole bucket is descending into the well. It is speeding up downward by 2 meters. You don't have to write this, by 2 meters per second every second. It is speeding up in the downward direction. Every second that passes, it's going 2 meters per second faster. So if it started from rest, it would go 0. Then 2 meters per second, then 4 meters per second, then 6 meters per second, then 8 meters per second. It's speeding up into the well in that fashion. And so over here, remember, this is not a force. That's just me reminding myself the acceleration is down. Let's do the problem. F net equals ma. Because my forces are not balanced. How do I know they're not balanced? Because I got an acceleration going down. If you got an acceleration, your forces ain't balanced. Who's the bigger force? Well, it's FG. You know that because I made it longer. I know you know that because I made it longer. But what if you were doing this problem by yourself? Would you know that FG was the bigger force? The answer is yes. How do you know? Because which direction is the acceleration? Down. So doesn't that mean the downward force has to be the bigger force? Remember, you will only accelerate in the direction that your net force is pointing. After you add up all of your forces, in this case 2, the direction of that addition of all those forces is the direction of acceleration. We call that addition what again? We call it F net. So since, let me make it real simple. How do I know FG has to be bigger than FT? Because I'm accelerating down. That must be the bigger force that's bullying this bucket to go down. It's being the bully. And we're going to say then that FG is the dominant force, but F net is made up not only of FG, but also an opposing force of tension minus FT. And that will equal MA. All right. Now let's solve for FT. It's very much like the last problem. We're just going to go ahead and add this over. And we're going to do what with our MA? Subtract it over, right? So add the FT, subtract the MA. And we get FG minus MA equals Ft. Ft equals whatever all that stuff is. So what is Fg? Remember the little equation I showed you right at the beginning of these notes. It's mass times little g. What's mass? 5 kilograms. What's g? Well, 9.8. We've been using that all last unit. And trust me, this comes out to be 49 big ones, 49 newtons. So we're going to have Ft equals Fg, 49 newtons. I just shifted the Ft to the front. You can do that. It's no big deal. We're still doing this. Minus my mass of 5 kilograms times my acceleration. And again, this is when we have to be a little bit more creative as problem solvers. Because in kinematics, I would have called a downward acceleration negative, yeah? But here, what did I decide to do? I decided to say, well, Fg is the big force, so I'm going to put it first in my Fnet, which I always do. And therefore, what I am saying is that down, without me having said it, what did I just say? Down is what? Positive. Right? And I know that is unnerving to some of you. You don't like it when rules change around. But that's why physics is not just math. You have to understand the concepts too. All right, enough with pontificating, if you know what that means. 10 newtons, 5 times 2, and this would be 39 newtons Ft. Upward, right? So there's 39 newtons up. Now, you probably have questions. You're probably understanding some of this, and some of this is confusing you, and I get that, right? And as we do more and more of these, you're going to know how to ask those questions, and I'm going to be able to give you answers. And before you know it, you're going to be really good at this process. But my gravity acting down was 49. My tension acting up was what? 39. So what's my Fnet? What's my Fnet? Well, isn't it just 10 newtons downward? Isn't the sum of all my forces 10 newtons downward? Yes, that's exactly what I did here. Well, I didn't do that in the problem because I was looking for Ft, but now you can see when I put Ft back in, it's just 10 newtons downward. This has been a long set of notes, but we're going over very important concepts that are going to carry through into our next unit when we get into 2 dimensions. All right, have a good day. I'll talk to you soon.